Okay, welcome to the session on succinctness, and I will say no more. And the first paper is succinct arguments for RAM programs via projection codes, and Akasha will present. Please.
Thanks for the introduction. This is a joint work with Yuval and Rafi. Let me begin with a brief description. Okay, yeah. Let me first begin with a brief description of succinct arguments. So here we have two parties, the prover and the verifier. The verifier is interested to learn about the verity of statements pertaining to NP relation R. Both the parties have statement X as input, and the prover in addition has a witness W. The parties then engage in a protocol pi where the prover proves the verifier that the relation R on this input's output accept. And at the end of the interaction, the verifier either accepts or rejects the statement. Now, the completeness guarantee is that if the relation R on this input's output accept, then we should always accept. And the soundness requirement is that for every efficient prover, if there does not exist a witness for which relation R on statement X outputs accept, then we should accept with at most negligible probability. And the efficiency requirement for succinctness that we have is that the communication cost should be polylogged in the witness size. Now, let us extend this notion for the execution of RAM programs. So here we have a prover who holds a huge database X, which is of size N. It commits to this database in the offline phase. Then later in the online phase, they run multiple instances of online phase where the prover proves multiple statements potentially on different RAM relations, and each of these RAM relations execute over the database X. Now, let us consider the ith instance of online phase. So here we have an NP relation Ri, which is executed by RAM program. And we are in this interesting setting in which the execution time of the RAM relation Ri is sublinear in the size of the database. That is, in its entire lifetime, Ri happens to access only a few set of bits of the database. Now, holding the witness Wi, prover with verifier runs the protocol pi to prove that relation Ri on database X with witness Wi outputs accept. Now, the completeness and soundness guarantee is same as we had for succinct arguments, but now we define it with respect to a database X. So here, what I mean is that if the prover is able to prove multiple statements to the verifier, then we can extract an effective database that can be proven to be consistent with the proven statements. The efficiency requirement is that the offline and online communication cost should be polylogged in the size of the database. Now, SRgram has several applications. For instance, it can be used to prove execution of sublinear time algorithms. Say, if we want to prove that machine learning training or clustering has been done correctly, then we can use SRgram. Similarly, it can also be used to prove search over data structures. For instance, we can prove that K records satisfy a certain range query in the database. It can also be used to prove statistical analysis. Say, we might be interested to prove some properties about a small connected component that satisfies certain constraints in a huge social network graph. So now in this work, we are interested in the following goals. That is, we want our SRgram construction to satisfy the following features. First, it should have a communication cost that is polylogged in the size of the database. Then the online runtime of the prover should be dependent on T. That is, it should be sublinear in the size of the database. And the third requirement is that we should make black box use of underlying crypto. That is collision resistant hashing in this case. By black box, I mean that our construction should make should make only Oracle access to this primitive, and we should not be dependent on the implementation of the underlying primitive. Or we would want an unconditional SRgram in random Oracle model so that we can compile it to a non-interactive protocol. Now, satisfying any two of the above three goals is easy. Say we are okay with the communication cost of our protocol being quasi-linear in the runtime of the RAM program in the online phase, then this is something we can do. So in the offline phase, the prover will first commit to the database using vector commitment, say Merkle tree. Then in the online phase, when it runs a RAM program R, it will open the commitment to the bits that are accessed by the database and give this openings to the verifier. Then the verifier can locally run the RAM program and verify whether the relation accepts or rejects. And say we are, however, this question becomes non-challenging. It becomes very challenging if we have zero knowledge proofs. And this has been the focus of recent works in literature. And say we are okay with the second constraint not being satisfied, that is, we have a prover whose online time is quasi-linear and then we can use standard succinct arguments and we should be okay. Now, if we want to make a non-black box use of CRH, then we can generate a proof that argues about the openings of the vector commitment. We'll explore this construction template in a bit more detail because this is where we build our construction from. So now this is our result. We come up with the first SR-gram construction that simultaneously satisfies all the three goals. In particular, our result is this way. There exists an SR-gram that makes black box use of CRH with the following efficiency matrix. That is, the offline prover runtime is polynomial in the size of the database. The online prover time is quasi-linear in T, that is the runtime of RAM program. And in our construction, it's not just the communication that is polylog. In fact, the verifier's runtime is also polylog, and it is an extremely desirable bonus feature to have. And now suppose we want to have a quasi-linear runtime in the runtime of the prover in the offline phase, then we can trade the online time, which now becomes quadratic in the runtime of RAM program. This result is achieved by instantiating the underlying primitive with a different code word. So this is the outline of our talk. So first, I'll describe what probabilistic checkable proofs are and its extension, that is PCPs of proximity. Then I'll discuss the construction template to obtain non-black box construction for SR-gram. And we'll observe a way to make this construction black box. And this observation will, in fact, pave way for the introduction of a new primitive, which we call projection codes. So I'll define this, the notion of projection codes and give a construction. And finally, we'll compile all the ideas together to form our SR-gram construction. So now let's start with what PCPs are. So PCPs, here we have an NP relation R that is computed by a Turing machine in time T. Here, I would like to stress that the time T is quasi-linear or superlinear in the size of the input X. And the prover will then generate a PCP proof proving the statement that relation R on input X and witness accepts. Then the verifier is given oracle access to this proof. The verifier, making only at most Q queries to the proof, will be convinced about the verity of the statement, and the soundness and completeness guarantee is standard, and it's similar to succinct arguments. Now, in this work, we make use of PCPs of proximity, which are similar to PCPs, except for the fact that here the inputs can be used, and that's the reason we don't give the input directly to the verifier. In fact, we give an encoding of the input, and we give an oracle access to the verifier to this encoding. So the verifier then would run at most Q many queries in total on and make oracle queries to X and pi, and then it will confirm the verity of the statement. Now, PCPPs with polylog verifier overhead are not known. In fact, PCPPs with proof generation time quasi-linear in the runtime of the RAM program T are known. Here, I would like to point out that for our result, that is for our requirement, that is we want the runtime of the prover to be dependent only on T, then the first set of results that is with low query complexity suffices. But if we want to have an asymptotically tighter result, then we can make use of the result of Benz-Sonata. Now, let us together come up with the construction for SR-gram using existing techniques. So here I'll not go to the construction of SR-gram directly, but I'll consider an intermediate notion which is easy to understand. That is succinct argument for sets. So here we have a database of size n, which the prover commits to in the offline phase. Then later in the online phase, the verifiers and the verifier and the prover hold the description of NP relation R and the description of set S. In addition, the prover holds the witness W. Now, say these are the set of bits that are accessed by the RAM program. Here the relation NP, the relation R is executed by a Turing machine, and the set S denotes the set of bits that are accessed by this Turing machine of this database. So the bits that are darkened represent the set of bits accessed by R. So first, the prover computes an encoding of this projected bits and let Y denote this encoding. Then the prover will generate a PCPP proofs with respect to the NP statement that relation R on projected bits and witness W outputs accept. And this this PCPP proof is generated with respect to encoding Y. And then, however, we are not done yet because if the prover is malicious, then it can generate a PCPP proof with respect to an encoding of arbitrary bits. So we need to bind this encoding to the commitment. So the prover generates an additional proof that is pi2, which shows that the encoding Y is consistent with the committed database. The prover will then commit to the encoding as well as the PCPP proofs using vector commitment. Then the verifier in its head will run the two PCPP verifiers V1 and V2. For any query that are asked by the underlying PCPP verifier, it will request for its opening to the prover. The prover will then send the value and the opening to the verifier, which the verifier will verify. And once it is verified, it will send the response to the corresponding PCPP verifiers. So this process is repeated for all queries of the underlying PCPP verifiers. However, we know the limitation of this construction, that is the proof 2, that is pi2, makes non-black box use of CRH, which is something that we would like to avoid. But so what if we have an encoding that we can apply in the offline phase and then commit to this encoding in the offline phase? Then later in the online phase, say these are the set of bits that are being accessed. What if corresponding to this set of projected bits, we have a set of bits in the encoding which actually form a robust encoding of the underlying projected message? Then we are done because we can just generate a PCPP proof with respect to this projected code word. And now notice that in this case, we don't need to generate an additional proof that binds this encoding with the commitment because the bits of the projected code word happens to be the bits that were committed in the offline phase. So then this exactly happens to be our notion of projection codes, which I'm going to describe next. So this is the new primitive that we introduced in this paper. So projection code is parameterized by 5 parameters, and it comprises of 3 algorithms: the encoding, projection, and decoding algorithm. The encoding algorithm takes as input a message X of length N and outputs a code word of length capital N, and the code word is denoted by capital X. The projection algorithm takes as input a sequence of K message coordinates, which are represented by the darkened bits, and outputs a sequence of capital K code word coordinates, which are denoted by capital S, and they are marked by the darkened bits in the code word. And now, additionally, we also have a decoding algorithm that, given a code word Y, will output a message Y, and if the decoding fails, it outputs bot. We want our projection code to satisfy the following robustness property. That is, this projected code word. This projected code word should form a robust encoding of the projected bits of the message. So put more precisely, if Y is delta close to the projected code word, then the decoding of Y should output the projected message. Now, let us come to our projection codes construction. So we built this construction using Reed-Muller encoding. Reed-Muller encoding is defined by a multivariate polynomial which is and it comprises of v variables, and the total degree of the polynomial is d. Now, given a message x of length n defined over fq, we set v and d such that the size of the length of the message is equal to v plus d choose v. Then we determine n fixed vectors in fqv that form a full rank linear system. Now the vector ci corresponds to bit I of the message. And these vectors are nothing but this setting of the corresponding multivariate values in that coordinate. So now at location ci, we set the value of we fix the evaluation of the polynomial to xi. Now, since the number of terms in the polynomial are n and we have fixed n evaluations, this process actually defines the polynomial, and then the code word is nothing but the evaluation of the polynomial over fqv. So now coming to our projection codes construction, the encoding is nothing but the Reed-Muller code. So given a message or a database X, we run the Reed-Muller code. We run the Reed-Muller code to obtain the code word. And then in the projection phase, we obtain a set of k message coordinates. And given this set of k message coordinates, we identify or determine the corresponding fixed vectors. Those were represented as C1 to Cn in the previous slides. So here, the fixed vector Pi corresponds to index Si. And then we use demultiplicative linear codes to extend these fixed vectors to a set of code word coordinates of length capital K. Now, the idea behind using a demultiplicative linear code is that if we were to evaluate the polynomial of degree d over this k coordinates, then it would actually form a robust encoding of the evaluation of polynomial of degree at most d for the fixed set of coordinates, for the fixed vector coordinates. And this fixed vector coordinates actually correspond to the projected message. So now the decoding algorithm is based on this intuition. That is, we make use of the spatial decoder algorithm of the underlying demultiplicative linear code and use it to decode the projected code word. And based on the intuition, we can argue that when projected code word, when decoded using the spatial decoder, will output the projected message. Now, based on how we instantiate the underlying projection code, we have two instantiation of our construction. If we were to use Reed-Muller encoding for projection, then we have a protocol in which the encoding time is polynomial in the size of the message, and the projection time is quasi-linear in the size of the message coordinates in the online phase. And if we want an instantiation of projection codes in which the encoding time is quasi-linear in n, then we can trade for projection time. That is, now the projection time would be quadratic in k. And notice that these two results actually these two instantiations are the reason why we had two different results for our SR-gram construction. Now, one might have a question that the problem that projection code solves can also be solved by locally decodable code. So the idea is that what we would do is that for each bit of the projected message that we want to locally decode, we'll ask for locally decodable queries, and the responses of the locally decodable queries for each of these coordinates, when concatenated together, would form a code word. But then the problem is that the encoding wouldn't be robust, and that's the reason we won't be able to prove a PCPP statement over this incorrect code word. I would like to point out that the construction that we have for projection codes is similar to the construction that Kramer, Zing, and Yon had for multi-point LDCs. However, the objective of both the primitives are very different. In particular, as we could see that the projection codes are deterministic, whereas LDCs inherently involve some randomness. And moreover, if we were okay with to have a polylog overhead and over multi-point LDC, then we can use standard LDC like the approach I described above and obtain a multi-point LDC with polylog overhead. However, there is no known reduction from LDCs to projection codes with quasi-linear overhead. So finally, we'll fix the final bit in our puzzle. That is, so we had so far construction about succinct arguments for sets. So we have to extend it for RAM programs. So we recall this classical result from literature. That is, for any RAM program that can be computed in time t, there exists a corresponding Turing machine that can simulate this RAM program in time t cube. And for the non-deterministic case, Gurvich and Chalet showed that this simulation overhead is quasi-linear in t. And we can use either of the two results for our final goal, and we use the asymptotically tighter to get asymptotically tighter result in our protocol. So, so this is the idea. First, we'll apply the reduction that we discussed in the previous slide and obtain the updated witness W dash and the bits that are accessed by the RAM program and the relation R dash that is computed by TM. And then using the projection, we determine the projected code word and generate the PCPP proofs. So that's our construction. And because of, as you could notice that the complexity of our result only depends on the underlying instantiation of projection codes. So now these are some open questions. You would have noticed that either we had polynomial time in the online phase or polynomial time in the offline phase. So we would like to come up with a projection code or a succinct argument for RAM construction in which the online and offline time are near optimal. And we would also like to add zero knowledge. One would think that it would be easy to add zero knowledge on this base construction. However, there are multiple challenges that need to be addressed. And so far, we are progressing on this work. Thank you.
Thank you. Anyone has a short question with a shorter answer? Expected?
Yeah, thanks for the talk. If you are okay with random oracles, do you get knowledge soundness in your argument, or do you have to do a bit more work? Like, can you just
we actually have knowledge soundness in our protocol. We are able to extract the underlying database.
Not without the random oracle, or with just with CRHFs?
Yeah, with just the CRH in the rewinding model.
Okay, thank you.
Okay, no further questions, so thanks again. And we'll switch speakers. So we are having a breakdown because the next talk is breakdown, linear time, and field agnostic snarks for R1CS. And Srinath Sethi will present.
All right. So this talk is about breakdown, which is a linear time and field agnostic snarks for R1CS. Let me begin by recalling what a snark is. It's a non-interactive protocol between a prover and a verifier where the prover proves that it knows some witness to some statement. For example, it could prove that it knows some value X such that SHA-56 applied to X results in a public value Y. In general, the prover is actually interested in proving the knowledge of some witness such that a circuit C applied to this witness along with some public input X makes the circuit output 1. A trivial proof system is one in which the prover simply sends this witness to the verifier, and the verifier just applies the circuit on the witness and the public value X. A snark achieves better properties than this trivial proof system. In particular, the snark proof is sublinear in the size of the statement that's proven. The time to verify this proof is also sublinear in the time to check that witness. So because of these two interesting properties, snarks have many applications. Turns out the prover time in snarks remains a key bottleneck. As a result, applying snarks to very large circuits involving billions of gates is quite expensive. This brings me to our work, which focuses on designing snarks with the fastest possible prover. Another focus of our work is also to build snarks that can prove a circuit defined over an arbitrary finite field. Let me give you some context about this. So in existing snarks, the circuit over which the finite field over which the circuit is defined requires this finite field to be either FFT friendly or be the scalar field of a fast elliptic curve. Because of this requirement, if someone wants to prove certain statements, for example, prove the knowledge of some ECDSA signatures over a standard elliptic curve like P256 requires the so-called field emulation. And this field emulation makes this proving even more expensive. So this brings me to our question, which is how fast can we actually hope the snark prover to be? As I mentioned earlier, the prover is proving the knowledge of some witness such that the circuit is satisfying. So a lower bound on the prover time is the cost of checking the witness, or what I call the direct witness checking. The direct witness checking procedure just takes the witness and the public I/O and checks if the circuit is satisfying. So if we let T denote the time taken by this direct witness checking procedure, then the fastest prover time that we can hope for is C times T, where C is some constant. Snarks with a prover time of C times T are referred to as linear time snarks. Because the snark is linear time, it cannot actually do certain operations. For example, it cannot do FFTs or multiscalar multiplications of size proportional to the length, proportional to T. However, doing Merkle hashing over a vector of size proportional to T is acceptable because of some prior work with novel hash functions. This operation can be implemented in linear time. So this brings me to our work called Brakedown. It's a linear time snark. It supports any sufficiently large finite field. For example, prime fields where the prime is at least 128 bits. This is the first implemented snark with either of these properties. The snark is plausibly post-quantum secure. It does not require a trusted setup. It can prove statements expressed in R1CS, but it also generalizes to other generalizations of arithmetic circuits such as CCS, which was recently introduced. In terms of efficiency, if we let n denote the size of the R1CS instance and lambda denote the security parameter, the prover time is order n field operations. The verified time and the proof sizes are both square root of lambda times n, where lambda is the security parameter. The verified time also scales with the size of the public I/O X. Finally, there has been a lot of subsequent works following Brakedown that provide efficiency improvements. For example, the recent work of Diamond and Poisson provides 2x improvements in prover costs and proof sizes. Some works also provide asymptotic improvements to proof sizes and verified times at the loss of some properties. For example, Orion Plus provides orders of magnitude improvement in proof sizes, but it requires a trusted setup and it's also not post-quantum secure. The rest of this talk is in 3 parts. First, I'll provide some background on modern snark design. Then I'll describe the design of Brakedown. Finally, I'll present some experimental results. At a very high level, modern snarks are constructed in 2 steps. First, they combine 2 primitives. One of them is a polynomial IOP, and the other is a polynomial commitment scheme. I'll describe what each of these mean, but at a very high level, they provide a succinct interactive argument of knowledge. And then this succinct interactive argument of knowledge is turned non-interactive through Fiat-Shamir transformation, obtaining a snark. There are some exceptions to this recipe. For example, most notably the linear PCP-based snark like growth 16 or folding scheme-based snark like Nova do not follow this recipe. So in the next few slides, I'm going to unpack this recipe, starting with polynomial IOP. So it's an interactive protocol between a prover and a verifier, where the prover wants to prove that it knows a witness such that a circuit is satisfying. There are a couple of things I want to highlight here. First, the prover's message in each round is a polynomial. Second, the verifier cannot read this polynomial in full. It can only evaluate this polynomial at a point it chooses. Finally, the verifier runs some checks that takes as input all the challenges that the verifier picked and all the evaluations that it computed, along with a description of the circuit, and it outputs a Boolean, indicating whether it accepted the prover's claim or not. So there are standard notions of completeness, knowledge soundness, just like in snarks. The verifier can also use pre-processing so that it does not have to read the description of the circuit as part of this final check. Another primitive that I want to recall is a polynomial commitment scheme. So here, suppose the prover has some polynomial G. The prover binds itself to this polynomial by sending a commitment to the polynomial. The verifier, instead of evaluating this polynomial, it sends the evaluation point to the prover, who then sends a claimed evaluation along with the proof that this claimed evaluation is consistent with the committed polynomial. Finally, the verifier just runs a set of checks involving the commitment, the point at which the evaluation was requested, along with the proof that was sent by the prover, and it outputs a bit indicating whether it accepts or not. It turns out that this is exactly the primitive that we need to turn a polynomial IOP into a succinct argument. Because there are a couple of things that this scheme provides, which is these commitments that the prover sends are short, and these proofs that are sent by the prover are also short and quick to verify. And it provides some standard notions like binding and extractability. So at a very high level, inside the polynomial IOP, instead of the prover sending the polynomial, it sends a commitment to the polynomial. And then instead of the verifier evaluating this polynomial at a point, it just asks the prover to evaluate that polynomial. The prover provides an evaluation along with a proof using the polynomial commitment scheme or the PCS. Finally, the verifier runs the checks that were done before. Along with that, it just verifies the PCS proofs. Turns out that this provides a succinct interactive argument of knowledge, which can be turned non-interactive using the Fiat-Shamir transformation. So there are many polynomial IOPs in the literature. There are also many polynomial commitment schemes in the literature. So we can pick one polynomial commitment scheme and then combine with any of the polynomial commitment schemes to get a snark. Unfortunately, most of these polynomial IOPs require FFTs of size proportional to the circuit size. So if we start with any of them, we don't get a linear time snark. There is Spartan, which provides a linear time polynomial IOP. But if you look at existing PCS, they either require MSMs of size proportional to the polynomial size, or they require FFTs. So if we combine Spartan with any of them, we don't get a linear time snark. In the rest of this talk, I'll describe the design of Brakedown and present some results. So at a very high level, what we do is we take Spartan's polynomial IOP and combine with a new polynomial commitment scheme. As I mentioned earlier, the prover time in the polynomial IOP is a linear number of field operations. The verifier time is a logarithmic number of field operations, and the communication is also a logarithmic number of field elements. In Brakedown's polynomial commitment scheme, the commit time and the prover's time to prove an evaluation are both linear number of field operations. The verifier time and communication are square root of lambda times n. So at a very high level, this polynomial commitment scheme builds on prior work. An implicit result in these prior works is there exists a linear time polynomial commitment scheme given a linear time encode, error correcting code. One unfortunate thing is that all the prior linear time encodable codes are completely impractical if you were to implement them. So there are two key contributions in Breakdown. One of them is it distills a linear time polynomial commitment scheme from these prior theoretical works. The second contribution is it provides a suitable error correcting code that's actually practical. So first I'll describe what our polynomial commitment scheme looks like, and then I'll describe our error correcting code. So I'm going to focus on univariate polynomials for simplicity. Breakdown actually uses this polynomial commitment scheme to commit to multilinear polynomials in the evaluation basis. Suppose we have a degree n polynomial. It can be represented uniquely with a vector of size n. And suppose the n is m square, then we can view this vector as a matrix with m rows and m columns. So the first thing that the prover does is it encodes each row of the matrix using an error correcting code that where the encoding time is linear time. And we also assume that this error correcting code is linearly homomorphic. So after this encoding procedure is run, the number of columns increase by a factor of row inverse, where row is the rate of this code. Then the prover just takes the columns of this encoded matrix and constructs a Merkle tree over that encoded matrix. And this root of the Merkle tree is the polynomial commitment. Of course, the prover's the Merkle root binds the prover to some matrix, but this matrix may not be well-formed. In particular, by well-formed, we mean that each row of that committed matrix is a valid code word. So to address this, the polynomial commitment scheme runs some testing procedure where the verifier picks m random values, where m is the number of rows. The prover sends a vector v that's claimed to be the weighted sum of this the original matrix that it committed to. The verifier runs an encoder to get a vector z, and then it performs some consistency check by opening certain columns in the encoded matrix. It may be easier to visualize this. Suppose we have m rows. The verifier sends these m random challenges. The verifier, with the help of the prover, obtains this vector z. Then the verifier picks certain indices in the vector z and checks if those values equal the weighted sum of values in the encoded matrix. And it reads those matrices by using the Merkle tree. So now I'm going to describe how Breakdown proves evaluations of committed polynomials. I'm going to use an example. Suppose we have a cubic polynomial. It can be represented uniquely with this 2x2 matrix. Then this polynomial can be evaluated at any point q by just using this, multiplying this matrix with two vectors, one on the left and one on the right. And these vectors are completely determined by the evaluation point q. So to prove an evaluation, what the verifier and the prover do is they just run the testing procedure, except instead of the random weights, they choose values from this vector L as the weights. The verifier does consistency checks with random column openings as before. Finally, the verifier just computes an evaluation by taking inner product between the vector v that was sent by the prover with the vector r to get an evaluation. At a high level, this PCS scheme provides completeness because if every row of the committed matrix is a valid code word, so is the random linear combination of the rows. So as a result, an honest prover will always be able to pass the verifier's checks. For binding, we want the property that if these checks pass with probability better than 2 to the minus lambda, then prover is bound to some polynomial of an appropriate degree. By bound, we mean that P must answer all the evaluation queries correctly. So at a high level, the reason this holds is because if any row of the committed matrix is far from all the code words, then with Y probability, random linear combination of the rows will also be far from all the valid code words. So that the prover will fail the testing procedure with very high probability. So if P passes these tests, then V knows that every row of this committed matrix is close to some code word. It turns out that this is sufficient to establish binding, and our paper has a full proof of this binding. So in terms of cost, the commitment size is a single hash value. So for example, 32 bytes in concrete terms. The proof size and verify time are both square root in the size of the polynomial. The prover time is dominated by two tasks. One of them is building a Merkle tree over O of n field elements, and the other is encoding square root to n vectors of each size square root n. In practice, this turns out to be a key bottleneck. So to address this, Brakedown provides a practical code. In particular, for a message of length m, the encoding time is approximately 17 m field operations under some parameter settings. And to achieve this result, we exploit specific characteristics that arise in our setting. For example, in our particular setting, there's no need for efficient decoding. In particular, both the prover and the verifier run only the encoding procedure. It turns out that this decoding is not even necessary for establishing knowledge soundness. Another thing that we exploit in our setting is we can actually work over large fields. For example, prime fields where the field, the prime is at least 128 bits. This is necessary for the polynomial IOP soundness. Finally, in our particular setting, we can actually work with randomized codes. So we don't need these codes to be deterministic. So I'm going to just provide a high-level overview of how this code is constructed. So for a message of length m, the code word has three parts. So it has x, z, and v. The first part is the so-called systematic part. It just copies the original message x. The next two components are computed in 3 steps. First, what we do is we multiply this original message x with a random sparse matrix to get a shorter vector that I'm going to call y. Then we recursively encode this vector to get the second component. Finally, we multiply the second component by another random sparse matrix to get the third component. So it may be easier to visualize this. So on the left side, I've depicted the original message. On the right side, I've depicted the encoded message. So the first component is the systematic part, which just copies the message. The second component is obtained by recursively encoding a compressed version of the original message. And the third part is just simply multiplication of the second component with a random sparse matrix. The paper provides a detailed analysis of this code. So in the next part of this talk, I'm going to present some experimental results. So we have implemented Brakedown in Rust with many optimizations to improve concrete efficiency. We also implement a variant of Brakedown that uses Reed-Solomon codes. This actually gives up the linear time prover, but it turns out it provides concretely shorter proofs than Brakedown. Both of these schemes are available from a fork of Spartan. Here's a slide that depicts the performance of Brakedown, and it depicts prover time, proof size, and verified times. It also shows 2 variants of Brakedown, one that applies to uniform circuits and another that applies to non-uniform circuits. There are a couple of key takeaways. One of them is Brakedown offers the fastest prover. The speedup, in fact, is significant compared to other schemes that are also plausibly post-quantum secure. For example, Fractal, Ligero, or Aurora. The Brakedown's proof sizes are actually quite large compared to many of the other schemes, but they can be reduced, for example, through proof composition as shown by subsequent perks like Orion and Orion Plus. So to summarize this talk, Brakedown is a linear time and field agnostic snark, and it makes 3 key contributions. It provides a linear time polynomial commitment scheme, which was distilled from prior work. It provides a practical linear time encodable code to instantiate this polynomial commitment scheme. Finally, we combine this new PCS with Spartan's polynomial IOP to get a linear time snark. With that, I can take questions.
Questions? Oh, you did a great job. No questions.
Yes. Thank you.
So we have now a little break for switching sessions, and then we'll continue at 2:55.